Okay, let's start the lecture. So we are going to resume the, actually I just came back yesterday and still have this kind of jet lag. So hopefully I'm awake enough to just talk through the lectures. So we are going to resume the linear regression, and today we are trying to finish linear regression and SVM, and hopefully that ends the classification modules. So basically, just to refresh what we have talked about before. So basically, we have this kind of linear regression problem, and it looks like very fundamental and very simple, but essentially really grasp the model behind it, and also the different kind of interpretations is really very important for a number of more complex models. So we actually, what we did is that we actually start from a very simple scenario of one-dimensional regression. So we are trying to find a function which is linear in x, and x here is a scalar value. So so this looks like what you will get from doing some kind of simple experiments, let's say physical experiments, and you only have one variables to change, and you can observe some kind of response. Okay, so and even in this simple case, we try to argue. I won't go through the details, but essentially we try to argue that if you view the whole problem in a vector space, so even for our case where x equal to just one dimension, but if we do this kind of things, we try to construct a vector x, and we actually work out some sort of solution based on the vectorized representation of x. We can actually easily generalize it to any dimensions. So so basically the same idea still holds if, let's say, you are trying to find a function, let's say y equal to some kind of function, estimate function of, let's say, x1, x2, up to xd, right? So if you want to do d-dimensional regression, essentially you are trying to say, okay, if there are a bunch of variables I can change, For example, although in many cases in our machine learning, it's not linear, but if you think about many of the machine learning algorithms actually have a lot of hyperparameters. So hyperparameter means for, those are the parameters that the optimizer, the module want to learn. You have to set it up by yourself. Okay, so you can think about all these x1 to xt are a bunch of hyperparameters of the models, and we actually can observe some kind of output, let's say the precision or the error rate or whatever things. Of course, in most of the cases, it's not linear, but let's say if we think they are linear, well, we can actually think about, okay, y is going to be some kind of alpha 1 x1 plus alpha 2 x2, alpha d xd plus some kind of bias term. Usually use small b to determine the bias term. So it turns out that we don't need to do this. I mean, it's very long and it's error prone if you really derive by hand. And sometimes, I mean, it also conceals the real message behind all these kind of things. So we can actually have another x, which is actually all the x, but you also, for example, here, I actually put a 1 here. So you can think about, I have a vector which is something like this. Of course, we do the transpose because when we talk about vector, it's always column vector. So the first dimension is almost like a dummy dimension, and then you also do these kind of things. Okay, and all the discussion below equally applies because we don't assume any specific nature of xi. All we need to do is to do the partial derivative with respect to each component of x. So here we actually define some kind of cost function, and generally speaking, they are actually called loss functions if you ever encounter some kind of books or papers. And here, if we just think about, if we don't talk about the loss function, if you just think about the cost function or error functions, in our binning method, we actually are using similar things. It's the sum square error. In some of the libraries, they actually do mean sum square error, MSSE, but essentially it's the same thing. It's just divided by the number of training examples or testing examples. So basically, that's equivalent because the number of testing or training is a constant. So minimizing that also is equivalent to minimizing the total error. Okay. I'll come to this later. So all the derivation we talk about is that we actually have this kind of interpretations. Okay. The key part here is that this part is actually, whenever you have a hat, it's an estimated quantity. So this is what our model thinks y should be. And this yi is the ground truth. That's the true value. And whenever you see this kind of summation of things multiplied together, essentially that's the standard inner product or standard dot product. Okay, so back to here, I think last time we mentioned that basically it means that I don't know what my model prediction should be, but if they are called y1 hat, y2 hat, and so on and so forth, the constraint I know that this column do the inner product with this guy should be the same as this column do the inner product with the ground truth. Okay, and you have another constraint where this guy do the inner product with this guy equal to this guy with this guy. Okay, so that's actually what this kind of model will actually give you. And you can see that later in logistic regression, we essentially have the same thing. The only difference is that here, the ground truth value is going to be a numerical value. Okay, so each component here belong to R, right? Belong to the real domain. Later, when we talk about the linear logistic regression, we know that this is not going to be numerical value. Instead, this is going to be, this is going to be 1 or 0, right? It's a Boolean value. And essentially what our model wants to predict here is actually a probability, pi. The probability, of course, is within 0 and 1. Okay? But no matter what you do, I mean, finally, similar things will happen. Okay? But of course, in that case, because each pi is obtained from a nonlinear transformation from each of the x, so there is no closed form solution. Okay, I mean, it's highly recommended that you actually go through this. I mean, because I didn't write out the actual equations, but if you solve the equation, you will actually find that because this is one-dimensional regression, we only have one variable. W is basically one-dimensional vector. I mean, actually, in our extended coordinate systems, W is two-dimensional vector. So there are two variables, W0 and W1, and then you have two equations, and then you just solve it. But later, when in logistic regression, it's the same thing. We have two variables and two equations or equalities, but the equality involves some kind of nonlinear transformation, and there is no way in the general case that we can have a closed form solution, analytical solution, but we do have a numerical solution. Okay. So I also mentioned it's not our focus, but just to convince you that if you want to do polynomial regression, let's say I think the curve by the formula should be a degree 2 polynomial or whatever, it's going to be in a similar vein. Okay, you can do something like this without changing anything if you work on the vector form. This is actually related to what we talked before, in the sense that this kind of mechanism, you can actually view it from another angle. You can think about, you can propose any model, okay? And for any model, for each data point, you are going to have an estimation. And we actually believe that the model we actually talk about is the real mechanism behind the observations, which means, okay, yi, the observed yi, so this is actually the observed one, observed value, should, in the ideal case, should be equal to the predicted value, okay? If we really found the true parameter underlying the data generation process. But in general, we do expect some kind of errors, okay? So basically, we need to put some kind of probability estimate saying that, okay, the real value, let's say you think about this is the almost like the real value if it really exists for this i's data points. We need to put out a formula to say, okay, given that my real value is, let's say my real value is 10, right? And what's the probability that you are going to see a value which is 12? Okay, so for numerical ones, I mean, if you don't have any domain knowledge, I mean, one of the simplest things you can try is actually fit a Gaussian. So you think, okay, for example, Gaussian only have, let's say if you talk about the standard Gaussian with a diagonal and actually identity covariance matrix, basically it's only the mean value. And the mean, we do assume that in most cases, the Gaussian is actually zero mean, which means it's an unbiased noise. And also, there is only one parameter, which is the sigma, right? So all you need to do is that you actually determine a hyperparameter sigma, and then you can actually quantify these kind of things, okay? But if you know that, let's say, if my real value is 10, but, you know, let's say you can think about any cases where, for example, if I know all the y's are integers, let's say the number of people are actually observed, and they actually follow some kind of Gaussian, not Gaussian, let's say follow some kind of Poisson or follow some kind of whatever distribution you already know, and then you can actually put a different probability model there, and from this angle, they all work, okay? This is because, as last time I mentioned, all these kind of models actually have some kind of, because the way you actually estimate this guy, the reason you estimate this guy is because you actually have a parameter. So you are talking about a function family. In linear regression, it's going to be a linear function. In logistic regression, you are going to see a specific form which applies some kind of nonlinear transformations there. But again, in every case, it's a family of functions. Okay? So it's going to be a large family. So each f, you can think about, for each x, sometimes we actually write this one belong to a big function family. So you can think about this as all the linear functions. And as long as, so if x is in Rd, again, extended with domain coordinates 1, this W is also a point in Rd. So given a particular W, let's say W1, this is actually a function, because it's not a scalar value. We're not talking about evaluating a function at a specific x. So you can see that here it's a function because it still have a variable x. Okay, but we can, if you think about a set, okay, we can think about this f as a infinite set, just like all the numbers, all the real numbers, all the integers, right? A set could be has infinite number of members, and in this function set, each function is actually a function. So which means, and in this case, you can plug in x, and they give you a particular value back. But the function is actually parameterized by a particular parameter. Okay, all the learning happens when we try to figure out which particular function within this big function family we should pick as our final model. Okay, and so if you do something like this, we found that any parameter w is possible. They only change the probability at a particular points. Okay, it's not very uncommon that, for example, just to give you some high-level idea, that if you are trying to consider W1 versus W2, and you actually have X1 and X2, okay? So under this one, it will give you Y1 and Y2. Let's say this is Y3 and Y4. I just abused the notation, okay? So it's possible that the real value you actually observed here is Y1 and Y2, right? So it's possible that this one is smaller. So this one is small, while this one is large, while this one is actually small. So you get the idea. So just as if we only have this function family only have two members. You can, for whatever strange reason, you can only choose parameter W1 and W2. And whenever you determine a Wi, you immediately get a function back. And with the function, you plug in xi, the model will actually give you an estimate of yi, right? Okay, my notation is not very pretty because I use 3 and 4, but you get the idea. So it's very possible that if you use W1, it estimates the observation is actually more explainable at the first point, simply because the model will say, okay, the real value should be this one, and the observed value is this one, and they actually only differ by a small amount. So in terms of probability, it's going to be more likely, right? And but the other student can argue that, okay, but if you choose W2, at the second point, the estimation is actually more probable. Okay, so that's usually the case. This is only for 2 points. You can imagine that this definitely will happen if you have many points. So you are trying to achieve a balance, just like negotiation. So it's almost impossible in real case that you can find a W which is close to everybody. Okay, you need to make the trade-off. So you need to quantify the probability, or in most of the cases, if you take the log property, it's going to be give you the give you the loss function. And basically, they actually say which one should I prefer, because each one actually have certain kind of weights. So what we do is that we actually need to choose a W which maximizes the entire probability of observing the Y1 and the Y2. Okay, so again, back to this case, you can think about, if I use W1, because the difference here is small, let me remove this one. You can think about this will actually give a probability, let's say 0.9, because they are actually very close to each other. But because these two, but if you use this W1 at the second point, Y2 estimates and Y2 are very far away. So the probability could be 0.001, right? And the same thing here, the probability, Because here, y3 and y1 is quite different. You can say this is only 0.1, let's say. And y2 and y4 are quite close, but not that close. It could get something like 0.7. Right? Now, if you really have this kind of case, the total probability of choosing W1 is going to be this one times this one. Okay, the reason you can do the multiplication is that if you go back to the very beginning slides of the classification, we do assume that every training example, actually, to be technically correct, every pair of training example and their labels are chosen independently and identically from an unknown distribution. Okay, so in this case, they are actually completely independent. So the probability can be multiplied together because two independent events, the probability of joint events, if the two events are actually independent, you can actually multiply them together. So you do the calculation here and you do the calculation here. So this will actually give you 0.7, and this I think will be no, one more zero. Okay, so you compare this one and versus this one, and it looks like this one is better, right? So that's why you choose W2. Okay, so all the formula later, if you just want to, it's really helpful not only just to look at the formulas. I mean, once you understand what's going on, I mean, the formula looks much easier to you. You don't really need to remember all the details. Essentially, you know what the formula tried to do. But before that, I mean, a very simple example. To me, this is already very, very simple. But if you have any problem, I mean, try to plug in some real numbers. Okay, that probably will help a little bit more as well. So basically, this is the procedure of choosing which W should we choose. Of course, in real life, I mean, there is actually infinite number of choices. Okay, but I mean, to simplify the scenario, you can think about the only discrete and a very small amount of choices. Okay, so there is yet another angle that we want to quickly cover. Again, this goes back to linear algebra. So this is kind of related to the case. Whenever we talk about linear algebra, there are actually, at least the fundamental parts, there are actually several main topics. From the engineering point of view, one of the, apart from eigenvector and eigenvalues, one of the fundamental things that we want to solve linear equations. Right. So we want to find, again, this is A is a matrix, this small x is a vector. So yeah, I won't draw the notations, but so basically we are trying to solve the system of linear equations where you have a matrix A times a column vector of x and equals B. Okay, so I won't go into detail, but essentially very similar to the scalar case. I think everybody can, for example, if we this is for the vector and for the matrix case. So this is for the matrix case, but I think if you have any problems, think about the scalar case. Scalar case, you can think about this is small a times x equals b, right? So I use a small letter. So again, here x is a scalar value as well. So what's the solution for x? Right, b over a, right? Anything I need to be careful of? Yeah, if a equal to 0, I'm in big trouble, right? But also, if both b equal to a equal to 0, there is another kind of trouble. Can you understand what's going on? For example, for this case, if a equal to 0, what's the problem I have? Huh? Yeah, don't think about the solution because essentially, so if a is 0, this means I'm trying to find x where x times 0 equal to some non-zero value of b, right? Is it possible? Of course, I mean you can think about b a as an infinite, positive infinite number, right? But if we don't think about that, this simply means there is no such x. Because every number, deterministic number, times 0 is going to be 0. And as long as b is not equal to 0, there is no such solution, right? So this is actually one case. But if b also equal to 0, we have another kind of trouble where do we have a solution? Yes. Not only we have one solution, we also have infinite number of solutions, right? Because this means I'm trying to find a 0, I'm trying to find an x such that x times 0 equal to 0. And any x in the real set actually qualifies, right? So we have infinite number of solutions. So basically, I won't talk too much, but if you are interested, hopefully you can actually see that ax equal to b in the system of linear equations, we also have 3 cases. Of course, the simple case is something exactly like this one. And if you write this one in a more standard way, it's going to be b times a minus. So if I just try to use the matrix form, it's going to be a. So essentially what you are doing is that you know that ax equal to b and a does not equal to 0, right? So we actually times a minus 1 on the both sides. So a minus 1, a minus 1. And this one actually give me 1. So that's why x equal to a minus 1b. Okay? And you do the exact same thing for the matrix. As long as this a is big A, and you can find the inverse of a big A. And by the way, finding an inverse of a matrix, of course, I mean, if we are assuming that the inverse actually exists, it's actually a fairly expensive one. But one of the special case, actually, I just attended a conference, and there is one paper which is essentially using this kind of trick, is that you can actually, for large matrices, it's very hard to find the inverse. It's very time consuming, and there are actually some kind of numerical problems as well. So what you can do is that you can actually do a decomposition. You can actually do a decomposition of Q lambda Q transpose. This is the eigen decomposition. And if you do the minus 1, it's going to be very easy. Okay? So anyway, I mean, so we already talked about some of the fundamental tricks you can actually play with matrices. Of course, there are a lot of sophisticated kind of ones, but I think yeah, these ones are sufficient enough. So coming back, for these kind of solutions, we actually need to deal with the case where there could be infinite number of solutions, there could be no solutions. And specifically here is that we are trying to solve the problem where there is no specific solution. Why? Because if you think about these kind of things, yeah, I should remove all these kind of things. Here, hopefully you get some kind of intuitive idea and you can understand what's going on. So we actually have the variable w, and it has only 2 numbers. You can think about this w as the x. Okay, the notation is a bit trickier. There are only two variables you can vary. Okay, but how many equations you need to satisfy? I mean, ideally, if I want each y to be exact the observation, right? This means, okay, if you times this w0, w1, it should be equal sign, exactly equal. So this actually means the first row times the first column equal to 6, the second row times the same column equal to 5, and so on and so forth. So there are actually 4 constraints. There are 4 equality constraints, and there are only 2 variables. Okay, so the number of variables is the dimension of x, and the number of constraints is how many observations you have. And as you would expect, I mean, in real life, I mean, in most of the cases, it's actually fairly easy to do a lot of experiments. So the number of constraints could grow quickly, but the number of factors, for example, if you want to predict some kind of sales or whatever, basically you think, okay, you can only think about finite number of columns or features, right, that I can use to predict the future sales. But the number of training examples can grow quite large. In fact, every year you actually get more samples. So it's general case that you have more constraints than variables. And this means there is no solutions which give you exact the observed value. So in this case, we are going to do something called the least square solution. And this is exactly our problem. So we are trying to find a W such that if you do the X on the W, this actually gives me Y. Again, this is all in vector format. Okay? We are trying to say that I want to find the W such that if using this W to do the prediction of Y estimate, the vector Y estimate and Y have the smallest L2 norm. Okay? In many cases, I mean, we usually start with L2 norm because it actually have good properties. And there are not only, I mean, some kind of theoretical properties, but in practice, it's easy to do as well. I mean, we won't delve too much, but basically, in many cases, we do want L0 norm, but it's very hard to do. So we actually do some kind of relaxation to L1 or even L2 or whatever. Okay, so this actually means that we need to interpret. I mean, one way to look at this problem is to look from a purely geometric point of view. Okay, so what is X times W? So X times W is, again, if we go back to this one, so again, W is W0 and W1, right? So one of the things we actually mentioned in the linear algebra is that whenever you have a matrix W times X, actually this is X times W, you can think about this from from sort of like a geometrical, from the algebra point of view, is that this actually says the result is actually W0 times the first column, 1, 1, 1, 1, plus W1 times 1, 2, 3, 4. Okay, it's nothing but a linear combination. So the combination components, the relative weight is actually specified by W0 and W1. So what you are doing that you are taking the first column of this matrix X and the second column, and you try some kind of linear combinations. Okay, that's very fundamental views. Because essentially W is the variable. So we are actually trying, you can actually take any W as long as it's good under certain perspective. So essentially you are trying to find, so all this XW does is that it's give you a point, it actually gives you a vector belong to the span of the first column and the second column of X. So if I write it in X1 and X2. Okay, so a span means, okay, if you think about these are the two bases, just like the Euclidean basis, that's the simplest base. But again, base does not need to be as long as they are actually 4 rank. Okay, so they are actually, for example, none of the columns are linear dependent on the combination. It's a linear combination of all the other columns. They actually form a base, and the base will actually span a space. So what you can do is that you can actually find any points, no matter which W you use, you are going to find a vector in this space. It's a span of the first 2 columns. Okay, and I just used this one. So you can think about it. This is actually one of the columns of X1. Let's say this is X1, this is X2. So again, you can think about it, even in a 3D space. What I'm trying to do is that you actually, whenever you give 2 vectors, right, it spans a hyperplane. Okay, in 3D it's easy to visualize, but again it equally applies to high dimension. So basically it's a hyperplane, and the span of it is actually any points, which is a vector, in this hyperplane. And in general, what we want to do, we want to find, we do have some kind of Y, which lives in the 4 space. Here, 4 space is 3 dimension, because that's, actually 4 space could be 4 dimension or 5 dimension, but there is no way I can show. So you can think about Y lives in a 4 space, while XW, for any W, lives in a space which is spanned by the columns of X. Okay? In general, there is no way you can actually make them the same. So for example, this is actually a y. This space is actually spanned by x times w. Okay? Now we are trying to say, okay, find a vector in this hyperplane or on this plane which have the smallest L2 norm to the y. And the L2 norm from geometrical interpretation is nothing but the Euclidean distance, right? So the problem from a geometrical point of view is that now, again, we are talking about four space is 3 dimension and the span space is 2 dimension, is that you have a 3-dimensional point and you want to find a point on a plane which is the closest to y. And we know that the closest point is going to be a projection, right? Should be a point which is called, let's say, y estimate, such that this vector, this line is going to be perpendicular to the hyperplane. Because otherwise, if you move a little bit, it's going to, if you move on the right direction, it's going to be slightly smaller. Okay, it's easy to, or you can think about the geometrical interpretation, right? So what we do is that if this vector is perpendicular to the whole plane, it's going to be perpendicular to any of the base vectors. So this means this vector, so let's call it, what's the number? Let's say, call it t, is going to be perpendicular to this vector. So this is x1. So t should be perpendicular to x1, and t should be perpendicular to x2. Okay, so whenever you have perpendicular, essentially it means, okay, if you take the inner product, so this is nothing but the inner product. So by the way, this is our t. So this is actually nothing but if you, this is the standard definition of perpendicular. So you take the inner product and they give you 0. Okay, and if you write all the equation here, and if you do some kind of rearrangement and write into a nice matrix format, this gives you something like this: x transpose times this t equal to 0. And if you do the solution, you actually will find a closed form solution of this problem. It actually involves some very useful concept called the pseudo-inverse. Okay, it's not a whole purpose, but I mean, that's why I didn't even, you can actually solve the equation by yourself and you can find the best W, okay? But basically, this just trying to convince you that what we are doing, that we are trying to find a solution which is closest to the observed values, and our solution is constrained in a low-dimensional space within the 4 observational space, okay? Okay, so let's move on to talk about the logistic regression. So the only problem with the logistic regression, I mean, the major difference between logistic regression and linear regression is that now the observed variable is not a real number. It is constrained to be 0 or 1. You can think about this as outcome of something. For example, let's say I always use the medical example, it's easier to understand. So let's say you have some kind of drugs or some kind of treatment or whatever, and the final outcome is whether the patient died or not, right? Or recovered or not. Let's make it more positive. So basically, what you observe is actually a binary variable. Okay? And it turns out that there are a lot of reasons why we can actually do this kind of interpretation, but one of the ways to motivate this is that what should we really estimate? What should the model really estimate? Because what we observe is 0 or 1. Okay? It turns out that what we want to estimate is the probability of seeing 1, or the same as seeing 0, because there are only 2 values. So you can model either, but usually we actually model the probability that, so we actually model the probability. So this is actually, I write an expectation because for technical reasons, but for the first interpretation, trying to get some kind of intuitive idea behind the model, it's nothing but given x, what's the probability that y equal to 1? This is the, if you have any problem, think about, okay, let's say toss a coin, right? The outcome is only 0 and 1, and what you really want to estimate is actually the probability that the coin is biased. What's the probability the coin is biased towards head? Okay, you should not directly model each and every outcome because it's going to be random anyway, right? So if you, so basically, I won't talk about why we actually do the explanation. This is mainly because we need to actually go over all the possibility, even for the same x. For example, even for the same x, you can think about for the same x, if you do the, if really the process has some kind of randomness, you are not always seeing that y equal to 1. Okay, you are only going to see a certain number of times y equal to 1. So again, for the binary case, it's actually the same. The property of y equal to 1 given x is the same as the expected value, but in more complex case, it's going to be different. Okay. So if we look at, let's always go back to this example. Hopefully this gives you some kind of idea. Now the only difference is that the observation is not going to be these numbers. Okay, you can think about this observation is, let's say 0, 0, 1, and 1, right? Again, I have a parameter w. Okay. Okay, so this is actually our x1, this is our x2, x3, and x4. So we are trying to say that for x1, right, I observe 0. So I can actually estimate what's the probability that for this x1, y equal to 1, right? So in this specific example, what's your answer? Should be, I heard some correct answer, should be 0, right? Why? Because throughout the data set, you have only seen this x1 once, right? And the only time you actually see it is actually 0. And hence, I mean, if you go with the maximum likelihood estimation, it's going to be 0. Okay? And you can do the same thing. This is going to be 0, this is going to be 1 and 1. Then the model is not interesting at all. It didn't have any predictive power. It's actually very similar to the case we actually talk about when we talk about converting from finite samples to a distribution. And one of the standard way to do that is using kernel density estimation, KDE, right? Although, forget about the technical detail, the whole idea is that this kind of estimation is actually very stupid in the sense that it only allocates a probability to the only case that it observed and nothing else. Okay? But of course, I mean, you can see that in some cases you can see 1, 1 again, and you actually this time you see 1. And if that's the case, the probability will be 0.5. So you get the idea. Okay? But in real life, I mean, especially if the dimension d is large, it's almost impossible that you actually will see two different objects they map to the same feature vector. By the way, this is X is usually called a data matrix. I think I mentioned it somewhere. Data matrix, where each row is actually a feature vector extracted for a particular object. So it's the same thing as in other models, let's say in decision tree or in naive Bayes, right? So that's the standard way we arrange things. So that's why it means, okay, this actually means x0 and x1, they are two different objects, but they happen to have the same feature vector. It's possible, but it's actually not very common. Okay, so how can we make the model a little bit more interesting? Okay, what we actually can do is to say that this probability is actually a function of x. Here it's actually x1. So the philosophy behind it is trying to say that now I know that for each x, whether I observe y equal to 0 or 1, it's going to be a probabilistic event. Okay? All I can estimate is actually its probability. But if I only have limited observation, and most likely only one observation, my estimate is going to be very trivial. It's either going to be 0 or 1. Okay? And it's very useless. And for example, even if we learn this kind of model, if I ask you to classify a new example, let's say this is 2, 3. Of course, I mean 2, 3 here is impossible. Let's say 1 and 33, right? There is no way you can do it because you haven't seen something like this before, right? So there is no way you can do any estimate. So that's the limitation of the model. If we just assume, each object can have its own probability, there is nothing we can learn. And hence, there is nothing we can generalize. Means, okay, we can apply it to more general cases. Okay, but in reality, we do believe that there are some kind of intricate patterns or relationship between different objects. Hence, we can do some certain limited predictions. So one of the things we do is that to say, okay, this probability is going to be a function of x1 if I really extract my feature vector to be very, very good. Again, think about the medical example. You can think about, okay, my first column is going to be the age. Second one could be the gender. Third one could be blood pressure or whatever, right? Think about any general kind of cases. So although I don't know what's the relationship of my outcome with age or gender or blood pressure, but I do believe they are actually related, right? Otherwise, I mean, if it's total random, there's no need. I mean, every time you go to see a doctor and they give you some medication, it really depends on your luck, right? There's no way you can do any prediction or hence the effectiveness of the drug. So what's the simplest model? The simplest model is actually a linear model. So we actually think this quantity is related to certain w times x. Again, don't use x1, although this is x1. So this is actually our model parameter. So this is actually the model parameter. Okay, this certainly makes sense. Okay, if you think about the x as only one column, so again, this is better. So let's talk about this column. Let's say this is age. Okay, so you have 4 patients. They are perfectly 1, 2, 3, 4 years old. Okay, you do whenever you put a w here, w is going to be a positive number or negative number. Okay, if it's a positive number, let's say the number here is, let's say. So if this is actually w equal to, let's say, 2 times age. So let's say this is age. This is, again, all one. So this is the artifact of adding a dummy column there. So this actually means the probability of a positive outcome, y equal to 1, we should say positive outcome, is actually kind of related to age, and the relationship is actually positive. What does it mean? It means as you grow older, right, it's more likely that your y, the probability is going to be larger. Hence, you are going to see a positive outcome. You see the relationship, right? Essentially, all the logistic regression and actually all this kind of general linear model will actually give you something like this. Okay, so hence, if you read all the medical news, they will say, okay, if you drink 3 cups of coffee a day, the chance of you getting some certain kind of, let's say, bowel cancer is reduced by, let's say, 35%. This is because the coefficient is actually negative. And if there is a high, you can also say if you drink more than, let's say, 3 cups of coffee, then let's say your heart attack probability is actually increased by 50%. That means the coefficient is actually positive. Okay, so you can actually make certain kind of interpretations of the model. So if you can buy into all these kind of things, again, I'm trying to just give you some kind of more deeper understanding. What if about the flu, right? I don't know if you every time, for this kind of flu, it's I'm talking about influenza, right? People actually die, rather than just quickly recover. And you can think about, I'm not a medical doctor, but I think infants and young people, young kids, right? And elder people are more susceptible to death, right? So if that's the case, if you just extract age, this kind of linear regression is not going to give you very good results, right? Because if you think about this is a probability, the probability, let's say y equal to 1 means, let's say dead, okay? The dead probability is going to be something like this, right? So this is age, let's say this is age 10, this is age, let's say 60. So if you are, let's say if you are more than 60 years old, the probability is no need for this one. So the probability is going to be high. Let's say this is 0.2, okay? And if you are below 10 years old, the probability is going to be high. But if you are in between, and if we don't know any other attributes, because here we only have one attribute called age. We don't have any attributes on whether you have some kind of other heart disease or, let's say, immune system disease or whatever, right? Then the best thing I can do is to say, okay, I have the prior knowledge that the probability looks like this, and hence, if you just use directly logistic regression, it's not going to give you a very good result. Because essentially, they are trying to use a linear regression, right? Maybe they find out this kind of lines, try to predict what's the probability. If everything else being equal, what's the probability of that? What's the trend of that probability changed if you change the age? But this is not the real picture, right? So you actually need to do some kind of feature transformation. Okay, what you can do is that if you, instead of age, you actually do something like age minus, let's say, 30, take the absolute value, right? I think then basically it will actually give you, so this is actually how away you are from 30 years old. So if you are small value, so this is actually called age prime. If you are smaller value, the probability of dying is actually small, and if you are longer, so you might have this kind of trend. So you can think about it as if you fold the two curves together. You end up with this kind of curve, right? And then you try to find some kind of linear function. It's much more accurate. Okay, so yeah, since we are talking about the model, so I just give you some kind of simple example, trying to convince you that, okay, modeling is very important, okay, because we are going to see many fancy models with a lot of good properties. There are a lot of mathematics or whatever theoretical property after it, but it doesn't mean that, okay, if you just use the model and apply to any problem, it's going to work, okay? It's very important to know one of the famous quotes in statistics, like that every model is actually wrong, but some are useful. So if you can find a model which makes some assumption, and the assumption is actually agrees with your data, then the model will perform well. Otherwise, I mean, even a very fancy model is not going to work very well. Okay, so here you probably buy the idea that I want to say the property of this one, too many circles. Yeah, so I want to model property of this one, and I speculate that it's going to be a linear function of my x. Okay. Now, if you just do something like this, it's not going to work. Why? Because, for example, if you think about this is 2 times age, the domain of this one is actually in real domain, right? That's the general case. But look at the domain on the left-hand side. It's always going to be between 0 and 1, right? So there is no way you can actually do it very well directly. Okay? So that's why we actually need to use a function which usually written in this way called sigmoid function. So again, if you use deep learning or neural network, they actually use one of the activation function is actually the sigmoid as well. So from the signature point of view, this kind of function takes a real value and return a value within 0 and 1. So sometimes we call it a squash. So sometimes you will see people saying that you need a squashing function. Again, if you take the idea of squashing function, I want my left-hand side to be -1 and 1. There are scenarios where you want something like this. There is another squashing function called tan-h. Basically, they will actually take any real value and as the input value, and the output value is guaranteed to be between -1 and 1. Okay, and with those kind of things, you can actually build. If you want the output value to be between 3 and 5, you can easily do it. Right. Okay, and the detailed sigmoid is actually very simple. I mean, there are formula there, but I think this picture is actually more important than anything. So what I want to say is that think about how we arrive here. On the left-hand side, this is to determine what your model wants to predict. Okay? And on the right-hand side, we actually think, okay, the value should be related to certain function of my observed feature x, because x are feature vectors. Okay, that's the basic idea of machine learning. I mean, we extract features, and hopefully from the feature we can predict something. Okay, if there is no relationship, or relationship is very low, or cannot be modeled, there is no way we can do any prediction. And in general, there is going to be some kind of mismatch in the domain. And all you need to do is just apply a function which, at least from the functional signature point of view, actually do the conversion. Okay? That's actually our model. Essentially, yeah, I cover all these kind of points. So there are actually certain names, the function, sigma function called the mean function, and also the sigma minus 1, take the inverse of the function, because you can think about sigma actually take a real value, come to some value, let's say y belong to 0 and 1. So this inverse function takes the y belong to 0 and 1, will actually give you a real value. Okay? This function is sometimes called the link function. Again, these are just the names, just in case you come across some kind of paper, they actually give you some idea on this. Okay, so so the actual function, as we talk about, is this sigma is nothing but this one. So you only need to remember it. If anything, although in practice you usually use this one, because if you want to do the coding, right, this is much easier to do. But if you want to remember, if you just want to memorize, this one is better. Okay, this is when we come to the softmax, which means we generalize the scenario to multi-class. You will see that this one is nothing but E0 times X. Okay, so you can think about this logistic regression as a special case of the softmax or max entropy classifier, where you always assign a parameter 0 to one of the class, actually to the class of y equal to 0, and you only need to learn the parameter w for the class of y equal to 1. So if you take this idea, this easily generalized to multiple class. If you have 3 classes, right? You instead of learning 3 vector w1, w2, w3, w1 is always 0. You only need to learn w1 and w2. Right? You only need to learn 2 sets of vectors. So if you remember something like this, and you just divide every denominator and the numerator by this quantity, and you end up with this one. So that's the story. Okay, finally, I just want to say that the decision boundary is actually, so basically, for example, the model will actually predict, again, if you look at the real examples, I don't know if you can see. So this is actually what we talk about, the observed value, right? We observe 0, 0, 1, 1. So our prediction value could be 0.7, this could be 0.3, this could be 0.4. I just randomly write some number, okay? Something like this, okay? So I need to know where is the decision boundary. For example, if I knew, for example, 1 and 33, my prediction is 0.75. Then I need to have my y4 or y5. Okay, I need to give an estimate value, and because the S value must be either 0 or 1, right? I need to decide whether this is going to be 0 or 1. And I think this is straightforward, right? Because the probability is actually just like the coin. If you believe the probability of seeing head is strictly larger than 0.5, your prediction will be head, right? So as long as this predicted value is going to be greater than 0.5, you actually predict y equal to 1. Otherwise, y equal to 0. So if you work out the mathematics, which I won't go into, it's a very simple thing, you will actually find that the decision is the same as whether the feature vector times this W greater or equal to 0. This is the decision boundary, which means if it's greater than 0, you predict y equal to 1. Otherwise, it's y equal to 0. Okay, if you just want a prediction label without the prediction probability, that's what you need. And from this, we actually conclude that this logistic regression, although they use nonlinear transformations, it's actually a linear classifier because its decision boundary is purely a linear line or linear hyperplane in the general case. Okay, it turns out that except for decision trees and the KN classifiers, naive Bayes also is a linear classifier. You can do some kind of derivation such that you end up with some specific W times the feature input vector X greater or equal to 0. Okay, let's have a 10 minutes break, then we move on to the training part. Okay, let's come back. By the way, the previous example about the influenza and its impact on, its relationship with age, this kind of folding idea is actually called a feature transformation. And actually, you can think about this as one kind of things of feature engineering. So if you recall in the pre-processing part, we talk about different kind of things of, we didn't talk about these specific ones, but we do talk about PCA and some other kind of transformations. So many of the transformation here is actually quite domain specific. So if you have the domain knowledge, or sometimes you plot the figure and look at the real distribution, this might give you some kind of idea. And also, when we talk about SVM, especially trying to generalize into kernel-based SVMs to add some kind of linear transformation, essentially we are going to use a very similar idea there as well. Although it's not folding, but it's generally speaking, it's some kind of feature transformation. So you extract some kind of feature, but you can actually apply some kind of transformations on the feature and to derive another set of features. So if you think about PCA, it's going to be like a linear combination of existing features. And if your original feature is 1,000 dimensions, and you apply certain particular linear combination, basically multiply a transformation matrix or projection matrix, you end up with, let's say, 10-dimensional features. Each one is a linear combination of the original 1,000 ones. Okay, so at least if you don't look at the nice property of the PCA, this is actually one kind of transformation you can do. And there are actually much more transformation you can do if you go to the nonlinear dimension. Okay, so in the rest, I probably will quickly go through the rest of the slides. So we already have the model. So the model here is essentially this one equals sigma of, this is exactly the same picture I drew using the real example. So I'm trying to say my model is that I do some kind of prediction on the properties, and the property is going to be a function of x, take some kind of linear transformation, and basically do a linear function of x, and then the function will give you a scalar value, and then you actually apply a nonlinear transformation to reduce it to 0 and 1. Now, we need to know which w it is. Okay, so I won't talk too much, but essentially it goes back to this slice. Okay, essentially the derivation here is, there are a lot of derivations there, but essentially they are trying to say, okay, I need to work out this one. But this one is actually very simple. And basically similar to this one, we need to make some kind of trade-off. So we need to work out the property. So this is actually the property. Okay. So the p here, the p is a function of x. So basically, it's the p here is actually, this is, I can write as a function of x, right? So the function is parameterized by w. So so this is actually a function of x. So basically, I'm predicting, my model is predicting for this particular x, I'm going to predict its property is p. And it turns out that my observation is either 1 or 0. So so I need to work out what's the probability that if my predicted property, let's make it concrete. So you get some, let's say this is 0.8, right? And what's the probability of seeing if my model is actually saying, okay, for this x, the y equal to 1, the probability of y equal to 1 should be 0.8. Let's say this is accurate. And then what's the probability that I see y, the real outcome observed, is exactly 1? It's nothing but p, right? It's nothing but, let's say I know the biased coin have a probability of 0.8 of having a head. Then I toss it and I observe the head. What's the probability for this to occur, right? It occurs with probability 0.8. Okay, so this is exactly p. And hence, the probability of seeing 0, the other side, that's the only two outcomes, either head or tail, or y equal to 1 or 0, is actually 1 minus p. Okay? So the likelihood of observing yi at this xi is a function where you actually think about it's actually fairly ugly because you actually need to look at it's almost like if then else condition. It turns out that we can write this function here, I mean, including the condition here, is equivalent to this one. So you can easily verify by yourself because the outcome of y, is either 0 or 1. So if y is 1, 1 minus this one is 0, and everything 0 is 1. So this part is actually removed, and the result is exact p. And you can do it the other way around. Okay, so this is generally speaking, this is a trick where you can actually write the probability of seeing particular yi by a particular model as a function, and the function is actually very smooth. I mean, sort of like you don't need to have the cases to handle different kind of cases, which is pretty ugly. And then we actually use the assumption that each data item is actually observed, sampled ID from the unknown distribution, and you just multiply. So this is actually the individual probability, and you go through all of them, all of the training data set. And usually, this is called the likelihood of the training data set. Usually, we actually work with the log of this guy. So you take, and usually we use the smaller L, log of this guy, and it will actually give you something like this. And then we actually need to do to maximize L, we need to maximize the log likelihood. We actually can take the partial derivative and do all the derivations, which I won't go through in detail. Actually, I think if I remember correctly, yeah, this function, this segment function actually have a nice property. If I remember correctly, it's like I think it has this property. So taking the partial derivative with respect to the input variable, again, input variable here is actually also have Wt of x, is actually equal to that one. So if you use that fact, the derivation here will actually be shorter. But anyway, I mean, if you do the right derivation, you end up with this kind of thing. And at the maximum point, it should be equal to 0. So if you set equal to 0, you end up with this kind of things, which is actually very familiar. So you can think about this one as our yi estimate. And this is the real yi. It's actually the observed yi. And this is actually just the jth column of x. Okay, so all you need to understand that this p of probability, the model will actually estimate some probability given the xi, and but what we observe here is actually a binary variable. Okay, but we should set our parameters such that if you do according to that particular model, you can calculate the probability on each and every cases, and they actually respect this kind of equality constraints. Again, if you have, let's say, 100 features, there are actually 100 constraints, because every time, so this J is going through all the feature, all the columns. Okay, exactly in the same way as linear regression. So that's why if you can easily understand linear regression, the only complication here is that this part is a nonlinear function. Okay, so there is actually no closed-hand solutions. So we actually use some kind of in the past there are actually specific algorithms developed for logical regression, but nowadays, I mean, usually you use some kind of a generic optimization method, and among them, the simplest one is actually gradient actually it should be gradient descent. So in most of the toolkits, what they do is that they actually take the, so this is called the log-likelihood function. Again, this is a function because the function's only parameter is w, the parameter. And usually we try to take the negative of it. So in order to maximize LW, equivalently we can minimize the minus LW. So minus LW is actually called NLL, negative log likelihood. So sometimes you will see the acronym NLL. So once you reduce to NLL, then you are just trying to minimize the NLL of the training data set. And the minimizing a function is typically most of the numerical kits toolkits will do. Okay, they will actually do the gradient descent. So in gradient descent, what you do, again, the formula here I think is ascent. So that's why you actually use the plus sign, because the gradient gives you the best direction, the direction where the function value grows fastest in a small neighborhood. Okay, that's the general idea. So if you do these kind of things, you actually update each W. So every time you move to a better point, such that the function value is minimized. Again, here it's actually maximized because we didn't do the negative log likelihood. Okay, and because the reason you can do something like this is mainly because of this one. So whenever again, although this is only in one-dimensional case, but you can easily find a multi-dimensional generalization. It looks very similar. The only difference that it's instead of derivative, it's replaced by the gradients and the Hessian. Second order derivative is Hessian. But basically, and this becomes a quadratic function matrix involved. But the general idea that within a small neighborhood, we can ignore all the, as long as x minus a is actually very, very small, it's a very small epsilon, we can actually ignore all the high order components. Right? That's the general idea. No matter how complex the function is, within the right threshold, a small enough neighborhood, the function can be approximated as a linear function. That's what this theorem says. And if you want, you can actually approximate as a quadratic function and so on and so forth. So if you see some kind of more advanced optimization method, like the Newton one, they actually approximate up to second order, up to here. So they ignore all these kind of things. So, but for this to be true, for example, this x minus a should be very, very small. So that's why you have a learning rate. That's why you should only move slightly, because locally it's going to be a linear function. So you can actually know where the function value minimized here grows fastest. But you cannot go too far away. Otherwise, it goes to the approximation doesn't hold, and hence it didn't always increase the function value. Okay, and the other more common variation here is that this is called the gradient ascent, which means you need to calculate this one. And if you remember, this loss function is actually a summation of the loss function of each individual points, r equal to 1 to n. So it's actually a summation over all the data sets. So whenever, in each step, whenever you do an update to the W parameter, you need to evaluate the gradients over the entire data set, which is very expensive, especially if you have a large data sets. So basically, we typically use a stochastic version of it. Again, there are theoretical theory behind it, saying that under certain conditions, and usually it's true in many practical scenarios, that if you run this long enough, and they will actually converge to the same results. Okay, although it converges a little bit slower. But what you do is that for this part, you don't need to calculate the loss function on the entire dataset. You only need to sample one of the xi and use the gradient there to actually move it. Okay, that's the whole idea. And in practice, somewhere between the version is called a mini batch. You can do mini batch SGD. So instead of doing a summation over n originally is the entire data set. In this version, you actually have, let's say, m equal to, let's say, 64 or 200 something. I mean, again, the mini batch size is something you need to tune as well. So the summation here is actually going through 1 to, let's say, 64, and each xi is actually randomly sampled. Again, in some scenarios, you actually need to design the mini batch, but sort of like a random sample from the data set. Okay? Here are the, don't worry about the Newton's method. We don't use the second order to do the optimization. So another important topic I want to cover is that this all looks very well, but I think last week we discussed about the overfitting. So that's actually a very important issue in practical machine learning and also in theoretical machine learning. The general idea is that, as I said, I mean, machine learning from mathematical point of view is nothing but selecting a function instance from a large function family. Okay? The general idea that if the function family is actually very, very large, so we actually need to define some kind of measure to measure the capacity, sometimes, capacity of the function family. Although each of the function family, let's say we usually, intuitively we know that linear functions, right, are simpler than nonlinear functions. Okay, because for any linear function, you can actually, it resides in the nonlinear function part. Just as we know that all the integers, right, it's actually smaller or contained in all the real numbers. Although both sets are actually infinite in size. But we still can say, okay, to some extent, I mean, certain notion of size of the former is smaller than the other one. So we do have some kind of, in theoretical studies, we do have ways to characterize what's the complexity, what's the capacity of the function class. But the general idea that if the function class is too complex, okay, it tends to overfit because you can easily find one instance, which is a function which fits pretty well on finite number of observations. Okay, so that's why we a typical way to do that, to avoid that, is to use regularization. Again, regularization is actually pretty simple in the sense that we actually try to optimize the loss function over the whole data set together with, so this is actually the loss, total loss. Actually, sometimes we actually do not use total. Sometimes it's very common to use average loss, the mean loss, but basically this is the loss. This actually means how much difference, if you like. Again, difference in not just simple numerical difference. Could be a difference in terms of probabilistic measures. How much difference the model prediction and the observation actually is. So what's the discrepancy there? And this is actually, say, this is actually the complexity of the model. So instead of minimizing this this loss function, we actually try to minimize the loss function plus some. So this is actually the hyperparameter. Lambda is a hyperparameter regulating the strength of the regularization. And then this W actually says, okay, what's the complexity of the model? So the typical W is actually used are L2 and L1. Okay, so if you look at the formula, again, this is the loss function. It's not a log likelihood. It's the negative log likelihood. So we want to, you can think about, we want to minimize the sum of the two functions. So let's look at when the function will actually have minimal values with respect to each component. So for the loss function, it's 0. It achieves its minimum, which is 0, if all the observed data is accurately predicted by the model. So there is no discrepancy, right? That's achieving the minimum loss, which is 0. And on the other hand, for the second component, it's 0 only when W equals to 0. Okay? So W equal to 0 actually means, for example, if we use L1 regularization, that's actually we can, in many cases, what we really want, the reason we actually have L1 is that we really want L0. L0 actually, you can think about another regularization here is L0. L0 of W is nothing but the number of non-zero coefficient in W, because W is a vector, and you can look at a number of non-zero components. But this is actually very hard to optimize for a lot of reasons, and we usually relax it to L1. Okay, so that's why we usually have L1. Another very common one is actually use L2. So it's actually usually believed that if W is actually small, it means that the function is actually smaller. The function is simpler because the function value, if you think about a logistic regression, let's say, the predicted property does not depends hugely on one of the factors, one of the features. For example, if my probability of this x is going to be sigma of, let's say 7,000 times age plus 1 times, let's say, gender. Let's say gender already normalized into some kind of numerical values. So this is going to be our W, okay? And if we use L2 or L1, that's going to give you a very huge penalty simply because this is actually very large. So we try not to use a very large coefficient. So in most of the books, they tell you that this actually corresponds to some kind of simple function, which is true. The real reason is that this actually corresponds to some kind of smooth function. So the function value does not change too much if you just change a little bit on age. Because if you have a large coefficient, as long as let's say age is a real number, so you take into consideration how many days within a year, so basically it becomes or even minutes or whatever. So you don't really want the probability value to change so drastically as long as you spend 1 more minute, right? I won't talk too much, but this actually, you can show that this actually corresponding to some kind of smooth functions. And so even if you are talking about a very large nonlinear functions, we actually restrict ourselves to a small portion of it where the function is smooth enough. Okay? So that's the theoretical explanation why we added these kind of things. And finally, the logistic regression classifier can be generalized to multi-class. And that's actually what we really want to remember. And actually, once you remember this one, you can easily remember the sigma model function. Okay? So this class of function, including logistic regression as a special case, they actually have some kind of very complex, very conflicting names. So some of the places they actually call it exponential classifiers or exponential models. Sometimes they actually call it log linear models. Okay, both are actually okay because you are looking at which way you do the derivation. So if you think about here, why is it exponential? Because the model essentially assumes that certain property of seeing these object values for a particular class decision, C is actually, so we actually assume y equal to 1 up to C. It's a classification problem. So we have C classes. This property is going to be a linear function of x, and but raised to the as the exponent of this e function, exponential function. Okay, so that's why you can think about this is actually rightfully called exponential model. But another way to call the log linear model is that if you take the log on both sides, log of this one, so this is called the log property. It's going to be log of exponential will actually be cancel each other off, right? So in other words, log of certain property that we want to calculate is going to be linear in x. So that's why it's called the log linear model. Okay, so again, it's very confusing because the same model, they actually call it different names, and the two names are just from different angles, but they are the same classifier. Okay, and in fact, this logistic regression or max entropy is only one of the simple models. You can think about if, for example, if we take the log probability, right? On the right-hand side, I don't really need to use a linear function. I can use other more complex functions. Or if you have learned, you can actually think this is actually a linear combination of, let's say, a factor of x from I equal to certain number. So a factor is actually, let's say, x1, x2, and x3. Let's say x7. So you just take certain combination of columns, and they actually, you can apply a function, and you can think about the final value is going to be a linear combination of all the factors. Or there are different kind of names, but this will actually give you a more powerful kind of models. It's related to the graphic models and some other more advanced models. But that's the general idea. So you are trying to model, all they want to do is to model the probability of, this is essentially the same as naive Bayes, or sometimes it's much easier to think about log probability, and you just model it as a linear function of certain things. Okay, and arguably one of the simplest model in this category is the linear, the log probability is actually linear in X itself. Okay, without considering the correlation between columns in X. Most sophisticated models actually consider correlation between columns of X or features of X, and hence it's more complex. And the two things, that's why from another perspective, you can think about why we do PCA or this kind of feature decorrelation. So if we do the decorrelation and make sure each feature is at least statistically uncorrelated, we don't really need to use a more complex model. Okay? But otherwise, you might need to consider correlation between columns. Okay, that's all for logistic regression. Okay, any questions? Okay, otherwise we quickly go to SVM. So that's the last classifier we're going to talk about. So we actually are, it's mainly based on the Stanford text, but again, it's not from the manual massive datasets. It's actually from Chris Manning's old IR books. It gives you a good emphasis on. Yeah, so the Stanford one actually mentioned more on the algorithm side how to do the sequential, optimizations. But this one actually did a better model in explain the models, because nowadays, you don't, even for me, I don't really spend time to investigate into the specific algorithm to optimize SVM, although there are actually some non-trivial ones. So some kind of disclaimer. So SVM is actually a very complex topic. It involves a lot of mathematics. We try to avoid most of them and just focus on the model itself. But eventually we need to talk about a few things such that you can understand what's going on. And our focus is trying to derive the model starting from some kind of geometric intuitions. This gives us some kind of primal form of optimization. And we don't talk about how to do the dual forms, but basically, in most of the cases, we actually solve the problem in a dual format, solve the dual problem. And there are actually theorems saying that under certain conditions, the optimal solution for the primal form and is the same as the optimal solution for the dual form. And more importantly, that the dual form is kind of efficient in certain scenarios, and also it generates well to the nonlinear generation called the kernel. So that's the plan. Okay, so for SVM, it also belongs to a linear classifier. So almost all the fundamental linear classifier. Actually, there is another linear classifier called perceptron. It's not very competitive in terms of performance, but it's very simple. It's almost like a very simple neural. But basically, we don't talk about it. Otherwise, for most of the fundamental linear classifiers, we already covered. So the general idea is that if we look at, again, two-dimensional case where we can draw something. So we actually have two classes and by the green dots and the black dots. And our job is trying to find a linear classifier. And you can show that the linear classifier is always in the form of this one. And if you know, this is generally corresponding to a hyperplane. And in two-dimensional, it's going to be a line. Okay? It's going to be a line in the space, but in general, it's going to be a hyperplane. So you can see that we actually have here this, and this are different kind of hyperplanes. So each one is a function, because each one corresponding. For example, for this one, if you fix this line, you can actually work out what's the W. So it's a specific function. Okay. So we have so many choices, and which one is the best one? So if you look carefully, this one is really bad because this actually makes one error, right? It actually, because on one side it's going to be green and on the other side it should be black, but this one is actually erroneous. So this one actually makes some error, but if you look at this one, for example, this one actually does not make any error, right? So everything else being equal, we won't consider the former one. We prefer this one. But even among the rest three guys, so this one, and this one, right? I call it 1, 2, 3, 3 different functions. Which one should we choose? Yeah, so many people actually say the middle one, right? I just want to throw some doubts into the whole thing, right? So what do you think the logical regression will choose? This is the first question. Again, it's hard to, because you really need to do the calculation to understand which one it chooses. But roughly speaking, you can feel which one it will choose. And also, what if we consider logical regression with, let's say, L1 regularization? So these are more advanced kind of questions, but you can actually think. Okay. But what I'm trying to say is that don't go directly for the intuition, because try to think about more options. As I said, I mean, every model is actually wrong. It's not I said. I mean, I quote, every model is wrong, but some are useful. So under certain scenarios, maybe this 3 is actually better under certain scenarios or under certain objective functions. Okay. For example, if you think about the regularization, so again, there are some kind of technical detail. I won't go deep into it, but for some reasons, we usually regularize on W instead of B. Okay, by the way, to derive SVM, we actually do not use the homogeneous coordinates. So here, the W, so each X is really the original X. So if each X is only one feature column, X and the W will be scalar values. And this is actually called a bias term. So in the logical regression, for mathematic simplicity, we actually absorb the bias term into the inner product or into the vector format. So there is no bias term, but implicitly W0 is the bias term. But here for deriving SVM, it's more simpler to separate the bias term out. So that's one thing. And for many models, they don't penalize on the bias term. Okay, whenever you do regularization, there are actually 2 ways. In fact, if you look at the SVM implementation in scikit-learn, there are actually 2 different. I think one is called the linear SVC, the other is called the SVC. They actually call different libraries, and their optimization function is slightly different. I think one of the difference is that the fast version, which is used liblinear, I think it's the linear SVC. They actually, when they do the regularization, they also regularize on B, if I remember correctly. The other version is a standard one, so it's slower, but it doesn't regularize on B. Okay. So if we regularize on W, and we use no matter, let's say, L1 or L2 regularization, we actually prefer W to be small, right? So what's the smallest possible W? Again, you can think about X as one dimension. It's easy to understand. Smallest W in terms of L1 or L2 regularization is going to be W equal to 0, right? So if W equal to 0, what kind of function you get? Yeah, the function looks like this one. Because it's a constant function. No matter what, because no matter which x it is, it's going to be minus b. But basically, b is a variable you can choose because we don't regularize on b, so b can actually move up and down. So what I'm trying to say is that if you really strongly emphasize on the regularization, if you regularize heavily, your line tends to be, at least in 2 dimensions, which you can visualize or understand, tends to be does not change too much with x. And if you recall, again, everything can be linked. If you recall, this looks very similar to the prior in naive Bayes. So again, naive Bayes, the idea that you actually have some kind of prior belief on the class probabilities, and whenever you see evidence, you adjust your belief, right? So if you only use your prior, it actually means no matter what evidence I see, what kind of xi I see, if you recall the naive Bayes part, I don't change my probability too much. It's exactly the same thing as adding a very, very strong regularization here. So the decision boundary or decision does not change too much with x, because again, w could be some value which is very small, almost 0. So unless x differ hugely, otherwise there is no difference in terms of the prediction. So it's almost like entirely relying on some kind of prior. Okay, but you get the idea. So one of the things we actually really want from the geometrical intuition is that we want some kind of hyperplane such that it's furthest away from either set of points, right? And assuming that the set of points is linearly separable. So which means there exists at least one hyperplane which can separate them, okay? So we consider this kind of case, and actually there are cases to generalize to non-linearly separable case. We don't emphasize too much on it. The library already handle all these kind of things for you, but let's focus on the simple case. So later you will see that this is actually called the margin, and in some textbook or papers they actually call the street width. So you can think about it, we need to build the widest street separating the 2 sets of populations. So basically there are, even in 2 dimensions, you can see that there are different ways you can actually find the hyperplane, and again, you cannot see the difference in width. Yeah, but actually there are actually some kind of difference in width. So our problem is trying to find the best hyperplane to separate them. So we need to formulate this as an optimization problem. Okay, the other important thing is that whenever we use that idea, it turns out that not every point in the data set, actually training data set actually is important in the final decision. So if you think about, if I choose this one, which maximizes the margin, which is this part, if that's really the final answer, you can show that it definitely will touch a set of points on the, let's say, rectangle data sets, and will touch a set of points on the circular points. Okay, because if it doesn't touch, it means you can further increase the margin, right? You cannot further increase the margin because it's rigid. It's touching something on both sides. Again, it's not always like 3. It's possible that this one is not here, this one is here, so only these 2 points are touching. Okay. Again, this is only 2 dimensions. In high dimension, it's going to be very complex. It's even harder to imagine. But those points are actually called the support vectors. And you can think about the hyperplane and the support vectors are actually sort of like chicken and egg problem. So if I know my hyperplane, I can uniquely find the support vectors. And the other way around. If I know who are the support vectors, I can uniquely determine the hyperplane. Okay, it turns out that when we do the optimization, we actually find the hyperplane, essentially the slope, if you like, in 2D, and then this will give us the support vectors. The reason support vectors are useful is that, first of all, this actually, again, is related to some kind of theoretical notion of complexity of the class. So the final decision function, which is the hyperplane, linear hyperplane, is only determined by the set of support vectors. Okay, it's finally we see the formula. You really need to understand this one. It's only entirely decided by the set of support vectors, and the support vectors are usually a subset of data points. In fact, there are parameters where you can choose. So if you choose a high regularization parameter, basically the number of support vectors will be smaller. Okay, so it turns out that if you have a smaller number of support vectors, this means, okay, your function is simpler, okay? Especially in the nonlinear version, when we go into nonlinear version. So this actually means the function will generalize, I mean, it's less likely to overfit. Whereas if you use no regularization or small regularizations, it tends to give you more support vectors, hence the function is going to be more expressive, which means the error will be lower, but you need to watch out for the danger of overfitting. Okay, so theoretically speaking, this kind of, you can control the number of support vectors so that you can actually sit on a right subset of classes functions, which actually achieve a good balance. And also finally, the final solution for the SVM, for the decision boundary, is actually entirely expressed by support vectors. So although we derive in the primal form where the parameters are W, but essentially the final thing is going to be related only to support vectors. And SVM has been shown to be very successful in a number of cases, especially in high-dimensional classification, for a lot of reasons. First of all, because they actually maximize the margin and use only a subset of points as support vectors in their model, they tend to not overfit that much, especially if you don't use a very powerful kernel. So this is actually very useful. And also in practice, its accuracy is pretty good. The only drawback is that later we talk about drawbacks, but running time is high and there are a bunch of things you need to consider as well. So what we do? So we want to maximize the margins. So we actually need to know there are actually two kinds of margins. One is called the functional margin, and the other is called the geometric margin. The other is called the geometric margin. So let's look at the functional margin. So first of all, we know that we are going to use a linear classifier. And in d-dimensional case, I mean, all the linear classifier looks like this. Okay, it's just like W transpose X is the feature vector, plus some bias term, and you take the sign. So if it's greater than 0, it goes to one side, and otherwise it goes to the other side. So we always talk about binary classification. SVM naturally is derived for binary classification, and there are standard ways to generalize to multi-class classifications. So the function margin is exactly removing the sign, because sign is sometimes, I mean, we use sign, sometimes they use SGN, sometimes you will see something like 1, let's say this WTX plus B greater than 0, let's say. So there are different ways. This bold function 1 means it's an indicator function. So if the predicate inside is true, it's actually take the value of 1, otherwise it's 0. So there are different ways to write these kind of things. So you can think about that if we get rid of the sign function or the indicator function, everything inside is actually the function margin. Okay. The reason we actually introduce this one is because, again, purely it's very similar to the logic regression. You can show that. One thing I want to mention that here we actually the yi is actually +1 or -1. It's not in logic regression. We actually derive the formula using the assumption that y is 0 or 1. Okay, because 0 and 1 is much natural in the let's say probabilistic explanations. But there are actually papers or books where they actually strictly use, because in standard machine learning theory, you always use, for binary classification, you always use -1 and +1. So there are actually derivation where you can actually do the same thing for the logic regression if you assume y equal to -1 or 1. Okay, but then some of the formula will look like different, but essentially they're the same. Okay, here it's the same thing. In theory, you can actually derive SVM using y equal to y belong to 0 or 1, but using +1 and -1 is much easier. Okay, so this is either +1 or -1, and it turns out that this actually times this one will actually always give you the margin, which is going to be the positive number. Okay, so this is a common trick to instead of writing a truncated functions involving if and then else, you actually can write it into a single piece of functions. So the problem with this margin, and we want to maximize this margin, the problem with this formulation is that if you look at the formula, what's the variable? The variable is essentially W and B, and we focus on W. I mean, so basically, if you found a particular W which give you a particular functional margin, and if you double the W, let's say you times 2 on each and every components of W, the functional margin will actually increase linearly as well. So because we want to maximize this functional margin, we cannot do that. Okay? The general idea is that this alone is not good enough because there is no way we can. There is a trivial solution where you set W to be any vector which is essentially infinite. Each component is infinitely large. So that's not what we really want. So we actually need to look at the. Oh, by the way, there are some kind of explanation on the functional margin. This is actually corresponding to how confident you are. So basically, if you are further away from the middle hyperplane, separating hyperplane, there is more chance that you actually think you belong to one of the classes. If you are just on the boundary, for example, if you look at the C is just on the boundary. Although it's classified as the positive examples, but it's done so with much less confidence. Okay, so it turns out that what we really want is actually the geometric margin. So geometric margin is exactly the distance, for example, for this point, exactly distance to the hyperplane. Okay, my drawing is exactly this part. Okay, we need to calculate this part. So if you don't want to know the derivation, basically the geometric margin is nothing but a functional margin. This is the functional margin normalized by the norm of W. That's all you need to know. But the derivation here, so I actually provided, so this is the derivation on the textbook, but I want to just do a quicker derivation. There are actually, if you know the inner product, so we already introduced inner product slightly in the linear algebra review. So in the geometric space, in the Euclidean space, the inner product is also the dot product. Because the dot product was derived from the geometrical intuitions. So what is A? Again, I consistently use inner product because it's easy to generalize to other cases, especially in the kernel version. But essentially for dot product, it's actually sometimes they actually write A dot B. But this is highly confusing until you figure out, okay, A and B cannot be multiplied together. So in matrix multiplication, you actually don't write a dot. So in many cases, you can actually write A transpose B. So that's the same thing. And also because inner product is equal to B and A, so sometimes you can say B transpose A. It's the same thing. Okay. Anyway, again, here we assume A and B are vectors. Okay. So the geometrical interpretation is that A inner product of B or dot product of B is nothing but the length of A, length of B, times the cosine of the theta between them, right? Okay, so you can think about cosine theta is nothing but this one divided by this one. And then you can use your geometry to work out the length of this one. Okay, that's actually one way to do that. But basically, what you do is that. Okay, so how to do that? It's actually very simple. In order to work out this kind of things, again, there are some kind of directions. So if we assume the direction is this one. So if we assume we want this kind of direction, so we want this vector. Okay, this is our, let's say we call it a t, okay? We call it t. So we actually want a t, and actually the norm of t, right? So as long as we can find the vector t. So we know that this vector A minus t equal to this vector, right? Remember how to do the vector subtraction, equal to this vector. And this vector is nothing but A, so basically this is actually nothing but A cosine theta, right? And this gives you the length. You need to remember that this is the length. And the direction is actually this direction, B direction. Okay? And then you actually, cosine theta is actually, you try to convert it into the inner product and do the calculation. Okay? So the other way is actually similar to the previous one, but the previous one, if you look at, it's a little bit messier. They use the functions. What you can do is that another way is that you don't use this one. You actually use the same idea using the so-called algebraic derivation, just similar to the previous one, in the sense that you don't know what's this vector, okay? But you know it's going to be lambda of B. B is the vector, so I directly use this one. So I don't know this one, but I know that A minus this one is going to be this vector. And this vector is going to be perpendicular to B, right? This is going to be 90 degrees. So this means if I do the inner product, it's going to be 0. Okay? So you work out this vector like this with a variable lambda, and you know that this vector should be perpendicular to B. And the inner product is actually, you have distributive laws and symmetric and so on and so forth. So you do the derivation, and you can actually easily derive the final thing, which is exactly this one. But another way to write this is, again, I provide some kind of detailed derivation there, but essentially, this is another way, essentially the same thing, but just doing some kind of simple geometric derivation. You can actually find that the distance, this is actually the margin. This is actually half of the margin is actually this quantity. So that's actually the same as, I didn't use the y because they're actually, otherwise you get a margin which could be minus or positive, but we actually want the absolute value. So a trick is that times y. Okay, so we already get geometric margins. So if you look at the geometric margins, the margin, so maybe I didn't call the margin, call the distance. So the distance for xi is essentially w x inner product plus b over w. So w is nothing but the norm of w. Okay, it's I just write everything in inner product format. So you can see that again this is xi. So you can see that this one is going to be right. So this is the distance of xi under a particular function to the hyperplane. So we actually want to minimize. We actually want to maximize the minimum distance for every xi. Okay. Actually, you should have a y corresponding yi as well. So just to make sure it stays positive. So I won't do the detailed derivation, but essentially it turns out that we need to fix one of the things, and it turns out that it's easier to say that, for example, if you look at the formula here, so again, if I change w, right? If I increase w by double my w, this value will actually become smaller because the denominator will actually become larger, but I mean, numerator will become, depending on the relationship between W and B, but it will increase, but the denominator will actually increase by a faster rate. So basically, if you just want to maximize the minimum distance, it's hard to do because W is actually a free variable. So what we do is that we need to put some kind of constraint. Of course, we can put a constraint on W, but more commonly, we actually put a constraint on the separation. So the general idea that we really want to impose the condition, again, you can show that the condition here is that every positive example, the function margin is at least 1. And for the negative ones, the function margin is at least -1. Okay? And actually, these numbers are just constant, just some kind of constant. So you can actually change this to 3, and essentially, it only change this one to be, let's say, if you change this to 3, I think this changed to 6. So again, if we just want to minimize some, I think later we want to minimize or maximize this row. So row is actually the margin, so we want to maximize the margin. The numerator being a constant doesn't matter. Okay, so the optimization is essentially the same. So that's why to make things simple, we just use 1. Okay, and here you got 2. Then we plug in the formula we derived before, and we can find, okay, under this scenario, the margin is actually 2 over the norm of W. Okay, as I said before, I mean, the numerator is 2, but it's going to be a constant anyway. So our optimization problem, the actual derivation is actually stated here, but that's not the main problem. So graphically, we actually postulate that, okay, my hyperplane is Wx plus B equal to 0. This is actually any instance, because W and B are variables. So any instance will actually give you this hyperplane. And I really want my optimization such that every positive point is at least 1. I mean, the function margin is at least 1. And every next example, the function margin is at least -1. And under this scenario, I want to maximize the geometric margin. Okay, that's the story. You don't really need to worry too much about the actual derivation, but the global picture is that we want to fix the function margin to be some kind of constant, and under these kind of constraints, we can meaningfully optimize the geometric margin. Otherwise, I mean, geometric margin is actually a function of the norm of W. So, yeah.
In other words, you want these margins to be
as large as possible. Yeah. While all the constraints here is actually satisfied. So there are some kind of mathematical derivation which shows that otherwise you are doing you want to maximize something, but then you do the minimization over all xi's, and you actually get some kind of margin of xi. So you actually want to do a max min, and under certain scenarios, you can actually do the exchange and do some kind of automation, and it will finally arrive at this kind of formulation. Yeah.
Just please draw what happened if we change 1 to 3. What would happen with the margins?
Oh, you mean this value to yeah, just as I said, I mean, essentially, if I change this to 2, let's say, if I calculation is correct, this one becomes 4. But anyway, we are going to maximize this one, so it doesn't really matter because that's going to be a constant. The only thing we can change is W, right?
But the graph in the next page, the marks will be the same.
Yeah, so that's why, yeah, it's hard to draw it on a picture, but the story is exactly your intuition. So we need to fix something, otherwise we cannot, like there are, everything is, how to put it? Just like a homogeneous system of equations. I mean, once you find a homogeneous, means there is no constant terms, and you know, on the right-hand side it's all 0. So basically, once you find a solution, every scalar value, I mean, let's say you times a constant on each of x, it's still a value solution. So that's why you need to fix some kind of things. Anyway. Yeah, maybe we can go talk about this offline, but the general idea that this is the formulation. And I think more importantly, we actually need to remember the final format in here. So this is actually more, because all the previous one is derivation trying to convince you why this makes sense. So here, our objective function, because if we want to maximize rho, maximize the geometrical margin, essentially we want to minimize W, right? The smaller W is, the better the margin will be. But the problem is that the W cannot be too small. If W too small, these kind of red points, so if they're small, all the red points will actually kind of be closer to the middle line, and they will violate the constraint that it's at least greater or equal to 1. Okay? So finally, you need to remember that this is the primal form. This is the primal form of optimization done by SVM. SVM need to find the parameter W and B such that we want to minimize something with these kind of constraints. So here, the constraints are inequality constraint. So remember, in the linear regression and the logistic regression, we actually have some kind of just a set of equality constraints, and we try to solve the equation, and we can find the x. But here, you can think about this variable is W, and we want to. You can think about this phi of W. Again, I don't like the function here, but we want to make sure that the norm of W is smallest. You can think about this is almost like the objective function or the scoring function. And all these kind of constraints must be satisfied. Okay, so that's the objective function we can derive from the geometric interpretation of the problem. But it turns out that this problem is actually fairly hard to optimize, and it turns out that we can actually use some kind of Lagrange multiplier to do some kind of to integrate the constraint into the objective function and take the partial derivative and so on and so forth. So there are a bunch of mathematical optimization theory behind it. But finally, what we do is that we actually need to find something like this. Okay, so this is fairly complicated. Let me explain this one. So you are trying to find an assignment of alpha 1 to alpha n. This goes through each and every data points. So these are actually each and every data points. So n is the number of data points, the number of points in the training data set. And our objective function now is a complex quadratic function. It's still a quadratic function because this is actually a vector form quadratic function. Okay? So if you expand it, it's going to be have a lot of cross. So you can xi, let's say k, xjk, and so on and so forth. So if you treat each component of x as a variable, it's going to be a quadratic function. Okay. So this just to show you that the objective function is a quadratic function, and now you want to maximize the function. Now the constraint here is actually like this. So first of all, sum of ai, yi, again, y are the labels equal to 0, and for all the alpha i's, it should be greater or equal to 0. Okay, so the actual derivation is not important, but I want you to observe that these are actually linear constraints. So essentially, what you are doing is that you want to optimize a quadratic function with respect to a set of linear constraints. And now your variable is not W. You see, here the variable is W. Here the variable is actually, if you like, it's a vector of alpha. It's actually, each data point actually gets a alpha I. And you will actually see that those alpha i's are non-zero and or non-negative. And many of them are going to be 0 in the final optimization. And for those alpha I, so for those alpha I strictly greater than 0, they give you the support vector. Okay? Yeah, so I won't talk about the dual form. Dual form is actually, probably I'll talk about it later when we talk about the kernels. But let's look at the primal form, okay? And let's understand this is actually a geometric, at least we can have some kind of geometric interpretation. We won't discuss the solutions, but many of the solutions actually still admit some kind of geometric interpretation as well. So this is the objective function we want to optimize. So we are trying to optimize a function which is quadratic in W. Okay, and then we have so many constraints, and you need to know that within the constraint, the only variable is W. Right? Xi, yi, b. Actually, b is also because b is part of the functions. So the yi and the xi, they are actually constant. These are for each different i's, you just look up the training data set, you get the xi and you get the corresponding yi, right? So these are actually constant. So here, you really need to think about, you need to change the gear. So usually we think about x are variables, but here you need to think about w as variables. Okay? And you can think about, again, I can only draw a two-dimensional case. Actually, I just showed the picture. So that's some picture I just downloaded from the internet. So it's not our objective function. But I just want you to see, so basically it's, basically this function is going to be something like W sigma W, W transpose sigma W. So sigma could be looks like a diagonal matrix, but you could have lambda 1, lambda 2. So lambda 1 does not equal to lambda 2. Because if this is going to be a identity matrix, the shape of W is going to be a circle. It's actually going to be a circle. Let's say this is the. So what you do is that you think about a map, right? Let's say forget about this one. So think about this object function. Let's say let half of W transpose W equal to some constant. Let's say constant 1.0, right? What you do is that you need to know where this W could be. And you need to know that this is nothing but a norm of W because it's easier to interpret. So that's why this optimization, from this point of view, is actually easier to understand. They are going to be on the unit circle, right? This is actually all the W such that its value is going, its norm is going to be 1.0, right? Let's say this is the origin of the coordinate. And this is going to be, let's say, 2.0. So this is 2.0, this is 3.0. Right? So you want to minimize, your objective function is to minimize the norm, right? So this means, okay, if you can go to the inner circles, you definitely want to go to the inner circles. Okay? But you can't. Why you can't? Because you have constraints. And let's look at the constraints. So let's look at one of them. So that's going to be y. I drop all the subscripts because it doesn't matter. W transpose of x plus b greater than equal to 1, right? So if you expand it, it's going to be W transpose yx plus yb greater than equal to 1. And essentially, it's going to be greater than 1 minus b y, right? So if you think about it, this is going to be constant, right? And yeah, actually, this is not good. I should derive in this way. So you can think about this as y times so y times W transpose x plus 1 times b. Okay, and this x can be moved to here, greater than 1, right? So you can view this as a vector in a vector. So you can write in actually, because it's already W transpose, so write it in this way, this transpose B, and this should be X, Y, and 1. So basically, if you think about W transpose B is going to be a row vector, and you append the other variable there, so that's going to be a new variable. It's going to be, let's say, call it a theta. Okay? And this is just going to be a constant vector. Right? So basically, it's going to be C times theta greater than equal to 1. Okay? Again, C is a constant. So what does it mean? Here, theta is the only variable, right? So C is actually any direction. This is C. And the C times C, this is actually the dot product, C dot theta, is that for any theta, the dot will actually be, this will actually be the dot product, like the length. The length should be greater than 1. So basically what you can see that if this is 1.0, then you draw a perpendicular line, and so this is the origin, and any points, so everything here is okay for our theta, right? Everything on the right-hand side of the perpendicular line, if you do the dot product, it's going to be greater or equal to 1, right? Anyway, this is just to give you some kind of geometry interpretation that each constraint essentially cuts off a linear, like a linear it's called half space. This is called half space. It just says, okay, the feasible solution, the feasible W, again, essentially it's a part of the new variable theta as well. It should stay on one half plane. And you need to satisfy for all such kind of constraints. So that's why you can see that one of the constraints says, okay, it should stay on this side, and the other constraint says you should stay on this side and this side. So basically, you can see that all the shaded area are the intersection of these half planes, and you can easily show that the final area is going to be convex if it's non-zero, if the case is not linear separable, you can show that there is no feasible regions. But once you have feasible regions, it's going to be the union, the intersection of all the half planes defined by the constraints, and they are going to be a convex set. Okay, and you can show that for this kind of scenarios, because your object function is still like a quadratic, and let's say this is your absolute minimum, which is 0. That's the coordinates. Okay, so the best you can achieve is actually this point, right? If I removed this, so these are actually, let's say, my objective function, objective equal to 1, this is equal to 3, 4, 5, just like as if these are the perfect circles. And because all the valuable solution is within this shaded area, you can see that the one I touch is here. Okay, so this hopefully gives you some idea of what is this kind of quadratic optimization with respect to linear constraints. Okay, and when we talk about linear constraint in general, we talk about inequality constraints, because equality constraint is easy to deal with. Okay, you can essentially reduce the number of freedom, because essentially it's like a solving equations. If you have an equality constraint, then it reduces the freedom of a variable. So originally you have three variables. If they need to satisfy one of the equality constraint, then essentially there are only 2 free variables. Okay, so the actual way to do the optimization is really out of the scope. It's actually called quadratic programming, and there are actually a lot of ways to do that, and it involves a lot of mathematical theory behind it, but that's it. Okay, now the next important thing is that, so what's the solution? We don't care about how to solve it. There are already toolkits to solve it. But finally, what we found is that the solution so basically, you can actually find the solution in the primal form, but these are actually not very useful. I mean, it's useful if you really wanted the W, The more useful part is actually this one. Okay, so the final best solution is going to be you solve the optimization problem, hence they give you alpha I for every xi. So for every data points, no matter the label is positive or negative, they assign a non-zero, non-negative alpha I, and it turns out that many alpha I's are zero. Okay, it's just due to the nature of the optimization. So we actually call the set of points such that the alpha I is non-zero called the support vectors. So non-zero alpha I means called the support vectors. So this fx, which means this is the decision boundary. This is boundary that you want to say, given a new x, I want to know the value. And actually, this is the function margin, actually. So if you really want to predict for x, it's just like a sine of this function. Okay? But the function here is simple enough, and I really want you to understand what's going on. So first of all, the summation only goes through all the support vectors. So even if I give you 1 million data points, and if you somehow tune the parameters such that only, let's say, 1,000 of them becomes support vectors, you only need to do the summation over 1,000 of them. Okay? That's the first thing. The second thing is that what you do is that this is my training data set. It's actually a support vector in my training data set, although it's called X, but XSV. And this is actually the point that I want to evaluate. You can think about these are the test, new points. And as I said, I mean, this transpose is nothing but X support vector and X. You can rule this one, and you have alpha SV. So SV goes with this one. So each one actually have a weight. And finally, you have, once you do the summation, and finally you have a bias term. Okay? So the general idea is that I want you to understand the decision is made for a new point in such a way. So it loops through all the support vectors. So support vectors, some of them actually belong to positive class, some of them belong to negative class. It doesn't matter. Each of them evaluates some kind of inner product. And in general, you should think about inner product as some notion of similarity, some notion of correlation, whatever. So it's kind of similarity. It's not a distance. So if the inner product is large, it actually means they are more correlated, more similar, so on and so forth. You should have this kind of notion. So basically, you can think about this is almost like some kind of KN classifier. But again, it's not using distance. It's using some kind of similarity notion. And it's using, it actually assigns different kind of weights. So first of all, each x is actually doing some kind of similarity with one of the support vectors. And the final value, similarity, is scaled up or down by the alpha values. And the alpha is actually non-zero. So it's always going to be, actually it should be a y. Yeah, I think I forgot a y. There should be a y here. So basically, you can think about, it's just like our KN classifier, if last time we should talk about. KN classifier idea is that you actually draw a circle, or in general, you can use any distance measures, try to find a neighborhood. And look, these are the most similar ones to the new test examples. And each one actually receives some kind of weights, and the weight for the positive or negative, right? So here it's exactly the same thing, except that your neighborhood is actually calculated by a global optimizing procedure rather than just locally, and predetermined by some kind of similarity notions. Here, they also use similarity rather than distance, and the similarity is actually the standard inner product. And later we'll see that it's possible to customize the similarity by using a different kind of similarity evaluation method. Okay, we'll quickly talk about it in the kernel version. And then finally, you do the summation, so you gather the vote on the positive side and negative side, and plus some kind of bias term, and then you see which one wins. Okay, so I think with all the derivation, here the message is pretty simple. It's just like that. Okay, so importantly, you can see that whenever you do the evaluation, it only involves inner products. Okay, this is essentially inner product. Okay, so I won't talk about soft margin classifications where essentially the previous model is derived based on the assumption that data is always linearly separable, but there are cases where it's impossible. So they actually introduce some kind of slack variables and do some kind of optimization. So yeah, I won't go to the details, but okay. So, but with once in the final version of the SVM without using kernels, so it's still linear SVM. The final objective function you are going to optimize is something like this. Okay. Again, this is, you don't need to know the derivation, but I just want to show the final. So the so-called natural form is the primal form. So you are going to, the reason you actually have this kind of C is because you actually allow some kind of constraint to be violated. Okay. So basically, you can think about this one. Everything here is called the empirical loss of L. So it means how well we fit the data. So you can see that what we are, so if this functional margin is actually greater than 1. So again, this is already times multiplied with y. So this is going to be the functional margin, which is always positive. Okay. So if it's greater than 1, so 1 minus something greater than 1, let's say strictly greater than 1 or equal to 1, it will actually be smaller or equal to 0. And then you take the max, so it will actually be 0, right? So this actually means if you classify under your model currently is parameterized by W and B, right? Under your model, if for a particular xi, the classification margin, the functional margin is actually beyond 1, then this point does not contribute any loss. Loss means discrepancy. Okay, so this means okay, there is nothing wrong with your choice. So, in other words, you can think about because of the max thing, you can arbitrarily push a positive example to be very far away from the hyperplane. Okay, but as long as it's more than one distance, like in the functional sense, one distance away from the hyperplane, you don't suffer anything. You don't need to suffer anything. But as long as it's smaller than 1, let's say it's 0.5, you do the whole calculation, let's say 0.7, let's say it's close to 1. So again, let's say this is the separating hyperplane. So you can think about a point. If a point here, the distance is 2.5, then this one contributes 0 loss. Whereas, let's say this is 1, this is 1, this is minus 1. So another point here, let's say this is actually 0.8, right? If you plug in the formula, the loss it contributes is 0.2. Okay? So then you know that basically the objective function is that we want to maximize, minimize the W, which maximize the margin, as we derived before. But with some kind of, we actually allow some kind of things to violate the constraints. But every time you violate constraint, because this point, although it's positive, but it's not too far away from the decision boundary, so they need to pay some price. But basically, this is actually allowing some kind of to see how much our model actually, agree to our observations. So this is actually our loss function. So we actually finally are trying to do a joint optimization, trying to balance the objective of maximizing margin, hence minimizing W, and also minimizing the training loss. Okay, and usually what we do is that if we divide the whole thing by C over 1, C is a hyperparameter you choose, then this one become. So this is actually 1 over C over this one, okay? And this is actually the normal kind of things. You can think about this is actually our loss, and this one is actually our regularization. Because this is actually our W2 norm, right? And the regularization strength is 1 over C, right? You get it. Although here we actually say this C is a regularization parameter, but in fact the way it's called a regularization parameter is because it's not because this is regularization term. You can think about this margin as the regularization term, because C is a constant you choose. So if you divide by C, it's going to be, this one cancel each other off. This is going to be 2C over 1 of this one, right? So this is actually our L2 norm. So this is actually our regularization parameter. And if you use scikit-learn, there is a hyperparameter of C, but you need to remember if C is larger, the regulation is actually smaller. Okay, if C is smaller, it's larger because essentially the regulation strength is 1 over C. It's not C. Okay, so mathematically, if you read a lot of paper, this part will actually be called a hinge loss. Okay, so I won't go through the details, but essentially the hinge loss looks like this red curve. So this one. Okay, because this Z is actually the model prediction. Okay, so so you can show that the final classification error is actually the so-called 0-1 loss. From the optimization point of view, this kind of loss is very hard to optimize because it's for one thing, it's actually not differentiable. For example, here there is no derivative. Okay, and here you have no gradient. Right? If you use gradient-based method, there is no gradient until you suddenly do a jump. So basically, it's hard to optimize such kind of loss function. So under this view, you can think about lots of models. In fact, you can actually model logistic regression as under the same framework, but they use a different kind of loss function. So the loss function SVM use is always something like this. So you can see that as long as I'm incurring some kind of loss, this particular data point will give you some kind of push. So because it's generally have a slope, so it will actually try to move to a, you can move the W such that for this particular point, the loss is actually minimized a little bit, right? And this will actually, if you think about the SGD, SGD actually get the gradients coming from a random sample data points. So this will actually ensure that the optimization will actually continue going on until, you see, this will actually stop. So once you reach this point, which is actually 1, reach this point, then there will be no gradient, which means, I mean, if you randomly sample this point, this already have large enough margin, it will say, okay, I don't have any opinion on W. Okay, I don't suggest any better ways to move W. Okay, so you can imagine that gradually speaking, if you run the SGD, and it's not really done in SVM as far as I know, but in many of the, for example, in some kind of neural network models, you can actually use similar max margin principle as well. So one of the net effect is that during the optimization, it will be faster and faster because many of the models, because every time you only move W by a little bit, right? So if you already classify a data points as highly confident, very far away from the distribution margins, eventually you don't really need to sample it again, unless your W changes substantially, right? Because every time you sample it, it will actually incur a loss of 0, and it doesn't suggest any way to move, I mean, slightly move W. So gradually speaking, your optimization will focus on points which are still currently not entirely correctly classified. Okay, so that's the nature of this kind of hinge loss function or max margin principle we give you. Okay, that's all for today, and next time we just finish the kernel part, and that should be all for SVM.